special equipment such as a Raspberry Pi or even a Wi-Fi Pineapple, while those can be used, this can actually just be executed by a normal computer. Every computer connected to a network, Wi-Fi network, switch network, anything else, follows some path through from the client computer to a web server to request information. Now, along this line, there's a number of things that redirect this computer's request in order to process it and provide what the client actually requests. This might be a DNS server, it might be the router that the computer is connected to within the wireless network, or it might be that server that connects to the very end. So this could be when the user requests a specific URL. This could be intercepted by having a fake DNS server. When it requests a specific IP, this could be intercepted by having a server which pretends to be at that IP within the network. So the man-in-the-middle attack is exactly that, a man-in-the-middle. Somewhere between the server and the client request, a device is sitting which is impersonating another device, or possibly multiple devices within this network. So while it's relatively easy to sit somewhere between a network on the router, or even if you had access to, let's say, an internet service provider level of information, most of the data we use now is encrypted using SSL, and this is ensured using HSTS, which is a technology which ensures that the website which we're accessing is actually the one associated to the certificate we're using for it. So rather than just passwords being in plain text, when we connect to a website like Facebook.com or something like that, the passwords we send are encrypted. While it's very clear to an internet service provider or even someone with access to a router what website is being accessed, passwords, text being processed isn't very clear. So in order to try and access this information, steal it, intercept it, we need to first be able to downgrade that level of encryption. So there are a few tools that we use to do this. We can downgrade the SSL encryption, which most web pages use, using a tool called SSL Strip. We can impersonate DNS servers using DNS2 proxy. We can impersonate ARP requests with ARP Spoof, and we can do this much easier with a framework called Man-in-the-Middle Framework, or MITM. We can also use Ettercap. We can provide phishing pages using PHP. We can inject JavaScript to try and execute code on a client device in order to request servers out of their web browser or cache or so on. So there are a lot of different ways to do this, but none of them are as effective as if text was just being transmitted in plain text, where we would have full view of what the user is requesting. So it's very good that these technologies exist, but for an attacker, they can still be avoided just using more clever techniques. Here are some different tools used in this example. All of them are available, run on Linux, and possibly OS X, some of them. Now, before actually attacking a network, and possibly even before connecting it, it's generally good to spoof a few things about your device. If your device has a very identifiable host name, that is the name that it tells the other devices on the network that is when it connects, you might want to change it to something much more generic. Any device can impersonate any other device. There's no authentication for the correlation between a MAC address and a host name and what the device actually is. So to impersonate something very generic, we might change someone's iPhone to the name of the device, despite it being a computer, and change our MAC address to have a prefix that matches the same one that an Apple device would use. Rather than this being something like a Raspberry Pi, which might have its own MAC address for a network card, or something that a network administrator rather would be able to very simply blacklist due to suspicion or standing out. Before we start targeting devices on the network, we'll want to find out a few things. What other devices are on the network, the location of the router within the network, as well as potentially what sort of website people are trying to access. So there are a few different utilities we can use to do this. Netstat, ARP scanning, as well as Nmap, which is a very popular port scanner for web attacks. However, it's also useful for enumerating a router or an internal network. So since as a man in the middle on the network, we're going to forward all of the network requests to our device, we have to enable IP forwarding, port forwarding, to actually allow our computer to just sit between other devices. This won't actually be enacted until we impersonate a device, but we do need to be able to process this traffic. We enable IP forwarding within our kernel of our operating system. We flush our IP table settings, and then we move port 80, where most HTTP traffic would normally take place on, to a port where we can control. This might be port 9000, port 8080, something that we can specify that isn't necessarily being required to adhere to the same standards of port 80, where HTTP traffic normally occurs. Now, at this point, we'll also want to start doing packet capturing. We can do this with Wireshark, TCP dump. It doesn't really matter as long as you're logging all network activities which go on. If you ran this without doing any man in the middle, it would just log all of your own personal traffic through a network. However, since we're going to try and parse everyone on the network's traffic, it will also log that through these same tools. So we use a tool called ARP Spoof first to impersonate the gateway. So before the router, we'll basically sit there, impersonate that router, and then forward all the requests straight through to the router. We're not doing anything to decrypt the traffic at this point, but because we're A, pretending to be the router, and B, logging all traffic that would normally be going through the network is going through us. It's probably still encrypted, and it might be slowed down by having that extra hop. But at this point, we can technically begin to scan and look at all of the traffic which is going through our device, or every device within a wireless or switch network. Now, we can also use different tools to do this to try and attempt to automatically downgrade encrypted connections. One of these is SSL Strip. It was written by Monty Marlinspike, who also developed Signal. He has done a lot for encryption. So we can just run that with only really one parameter, just specifying what port we've attempted to move the normally encrypted traffic to. So if we set it to 9000 or 8080, we would use that as our parameter. We'll also want to use DNX2Proxy. We can use this to configure a few different things, maybe to redirect certain websites to certain addresses, but within the scope of a man-in-the-middle attack for decryption, it will just impersonate DNS servers automatically, all that are requested. We don't even need to run it with arguments. We can just run that Python script. So after leaving this to run, we can scan through the data. We can look for things like password, PWD, password, and post functions, different things that websites would use to authenticate. Now, normally these would be encrypted, and we wouldn't even necessarily be able to pick up on the fact that these are passwords. But since we've downgraded SSL traffic, and websites which haven't properly configured HSTS will generally fail this, we can actually decrypt people's passwords in plain text without having to scan for hashes or anything like that, that we can actually view those passwords from our log files for anyone on the network that access the site which happen to be vulnerable. And this would be visible to the user, but only in the lack of an S after HTTP in the URL bar. Generally, some browsers would alert the user, but this is an alert that is normally ignored. Here's a demo of, let's see. So here's the order of some of the tools that we run. We enumerate the network first, which is you can see going on in this upper left window, seeing a few different devices which are on the network. We can get their MAC address, their IP within the network, and so we're going to target a specific device. We find our network gateway and feed that into our ARP spoof, so that way we can specify the location of the router which we're attempting to impersonate. We'll also, in this case, specify the IP that we're targeting, but this could be applied to a whole network or a specific person within that network. We flush our IP tables configuration in order to actually enable port forwarding, and then also set the port forwarding to port 9000 in this case, and also move port 53 to 53 again, but through our port forwarding. We can run ARP Spoof at this point, as well as start our network logging. So now, down here, using TCP dump, we're logging all the traffic on the network, and we've just started spoofing the router location. So finally, we run DNS, or second to last, we run DNS2 proxy, which spoofs a few different websites, as well as spoofing DNS requests. And finally, we run SSL Strip to try to downgrade SSL requests. Now, with that all running, we'll basically log all network requests going through that during this time. Once we actually leave that to run and someone logs into something, we can search through the log file for something like password. In this example, login name, username at email.com, password, dumb password. But it's that simple. After running all those programs, which is admittedly a bit of a clunky way to do it, we can scan and find passwords, credentials that were transmitted over the network in plain text without any need to even decrypt them. Now, we can also automate some of this process using man-in-the-middle framework. Man-in-the-middle framework has lots of plugins to also do other functions, but for the most part, it's configured within a configuration file, and using just a few parameters at the command line, we can run almost the same process we did before. So by specifying the interface, by specifying the HSTS flag to downgrade SSL connections, by using the spoof and ARP flags to spoof the ARP gateway, and then finally the IP, which we're trying to target. This can execute almost the exact same thing. However, it would also need to be logged within Wireshark or TCP dump or another program. Now, this doesn't work for every single website. Websites like Facebook, Gmail, any very large website generally has a file within an HSTS configuration that's distributed with every browser downloads. Someone who downloads Chrome, Firefox, Internet Explorer actually has a rule within that browser which requires it to use SSL and confirms it. It kind of has a pre-shared key. So this won't work for those websites just on the basis that we can't change those browser presets. What we can do is impersonate a server further down this line of man-in-the-middle requests by actually impersonating the server which they request. We can do this using DNS. First, we'll need to actually have a PHP, HTML, some sort of web stack sitting on the network, which impersonates a real server and can act like it. We need to have a single IP for each given one, so we need virtual machines if we want to impersonate multiple websites or multiple computers connected to the network. But the laptop or device which we have connected to the network is no longer just a client on that. It is a server within that network, and we can redirect other users to say that that server isn't at 126.0 or whatever local IP address. It would actually be at google.com or any URL we want to say. We could also do this as a captive portal to say you need to log on with your Google account to use this Wi-Fi, which is something that most people will use because many Wi-Fi networks actually require that. We can clone this manually using PHP. These are a few different things that we would do in order to do that. This form right here is normally what a PHP password request would look like. But instead of the post.php request as the action, what we normally send is to their web server. So instead, this writes to a file which we control and we can log. So using Ettercap, we can actually configure our rules for what our server is redirects to. In this case, my device was 192.168.0.105, a normal device on the network. However, using this Ettercap configuration, we say gmail.com actually resolves to me on that network. Anything.gmail.com would forward to me. I host that phishing page on my computer just using PHP. It has an integrated server module. I bind it to port 80 at my IP address within that network. And then I run Ettercap, so that way any other device on the network which requests that actually gets my computer and my server, which I have full control over. So So first we'll look at what this actually looks like on the user side of the person running the attack. We start first our server here using PHP. We run Ettercap, it only takes a second to go. We have our Ettercap configuration down here, which is forwarding Google requests. And basically it's running. And right now, anyone who looks for gmail.com, like someone just did as shown in the log, will actually get my computer rather than the real gmail.com. And for the client, this looks almost completely seamless. Here we have our client attack device. They type in gmail.com, and it says gmail.com and the address bar remains there. But until we switch to this page where it's very clear that this is login.index.html, not the real page, and we send this login information that redirects them just to Google's homepage, there was no real indication of anything wrong. The URL in the URL bar wasn't a phishing page, it was gmail.com. And to the user, it would be basically indistinguishable. So, after running that page, after they log into our fake gmail.com, we can go through our PHP logs and see that they use email lethal, password, done password. While we can only do this for really one website at a time, if we're very clever, or if we have a network where a lot of people are accessing something specific, or even just use multiple virtual machines to spoof very common websites like Gmail, Facebook, Yahoo, we can actually catch a lot of passwords, and most people won't be able to catch what they've done until sometime after. And if there's no actual wireless connection to their service, it might take them a while to change their password. We can also integrate this using Beef Framework. Beef Framework is a JavaScript-based framework that we can basically inject JavaScript hooks and do things remotely, almost like a rootkit within our browser. In this example, I encode the IP because a standard decimal IP, or standard IP with 4 octets of 3 digits or less, of less than 255 as the digit number, is generally caught more easily by a firewall. Something like this, where it says 192.168.0.104 on port 3000, might be caught by a firewall if the user requests it, or by a browser or something else. So we can actually encode that IP as something like this, which simple firewall rules might actually miss, that this 0x hexadecimal digit, which resolves to our IP, will actually just be completely missed by a firewall. And while we host on that server our JavaScript hook, which will run our Beef injection point. So first we start our Beef server. If it's running at our place on the network, we'll have used our code that we created in the previous step in order to reference it. And then we run man-in-the-middle framework again, using some of the same parameters as before. We specify our network interface, downgrade SSL, spoof the ARP gateway, and also inject this JavaScript into every single web page that the user requests. After the user goes to any web page, and as long as JavaScript is running, we'll have them hooked and visible within our Beef framework. We can see them right there. Now, with JavaScript, especially JavaScript that we can run at any time remotely, we have a lot of control and a lot of potential to capture things which should normally be encrypted. We can try and establish persistence too, so even if they leave our page, we can continue to have their browser. We can redirect them at any time from one page to another. We can fake updates like Adobe Flash and get them to download something. We can send them to a fake phishing page. We can detect different things like pop-up blockers. We can take photos with their webcam if they allow it. We can detect antivirus. We can do a ton of things with JavaScript. And these are the same things which could be done on any website which is running JavaScript, which is why I highly recommend using NoScript, because even though JavaScript provides a lot of useful functionality, it is extremely overpowered within even a semi-sandbox browser environment. You can have a lot of control over a user using JavaScript. So with this in mind, man-in-the-middle attacks are still a very real threat, even with encryption. Partially because of social engineering, and partially because of these semi-core implementations of encryption, where they can still be redirected at the ARP spoofing level rather than necessarily at the server level. Or we can inject JavaScript rather than actually trying to decrypt SSL. And for example, these sites I had tested failed to implement TLS or HSTS properly. eBay, Stack Exchange, Chase.com, Bank of America, HSBC, several banks actually fail entirely to implement SSL properly. So if I was on a network and someone decided to do their banking, I could run that very first attack we ran and capture their banking information in plain text, which is very dangerous, and it is partially their fault and partially the fault of the protocols. So overall, man-in-the-middle attacks are still very dangerous, even if they have to be changed somewhat to update to our different encryption standards. But overall, it's a very useful attack that continues to be dangerous.